Okay, let's get started. So welcome to lecture 4. Yeah, lecture 4. Um, Today is our first lecture. We're actually going to talk about reinforcement learning. So I've been cheating you thus far by talking to you about imitation learning. But today we're going to talk about reinforcement learning at long last. And so we're gonna get we're gonna get what we promised. So today we're gonna talk a little bit about model-free reinforcement learning, specifically policy gradient. We talked about the simplest version of policy gradient today, and why it's not good. And then we'll go ahead and work up to PPO, STRPO, and fancier methods like that. Yep. So how many of you all have heard of policy gradients? Yeah. Okay. So if something is boring, just like shout out boring and we'll skip it. Right? But just to recap from our first lecture, the goal here is to do reward maximization. So you want to find the parameters of your policy phi theta, which when you sample in the environment, actions from phi theta, transitions from your transition dynamics, you maximize the sum of rewards. And so in imitation learning, we talked about, okay, we're going to get expert data. You're going to use that expert data to infer those parameters data. Today, we're going to try and do reinforcement learning, which is different because we're not going to assume access to expert data. We're only going to assume access to sampling from the environment and access to the rewards. Right? So the nice part is we don't assume access to expert, but we will assume a reward function and we will assume environment sampling access, right? The goal is still to obtain a policy phi theta, and the goal is now to maximize the sum of rewards. Last time we talked about how in imitation learning, the goal is to minimize the divergence from an expert. There's no expert here. The goal is just to maximize the sum of rewards. Right? Okay, so we talked a little bit about finite versus infinite horizon. I'm going to be a little sloppy in this lecture for the sake of notation, but we'll just kind of try to cover this objective, which is maximize the expected sum of rewards for a finite horizon problem. No discounting, but you could always add in discounting. It's not going to change anything. Okay, so there are a few assumptions we're going to make, right? These assumptions are assumptions. They don't have to hold in all problems. So an RL textbook will try to convince you that this is like gospel, but it's not, right? So remember, these are assumptions. And in the real world, you can break these assumptions, right? So first assumption is that rewards are additive, right? Which means that what you want to do is you want to maximize the sum of rewards, and rewards are Markovian. They're just defined on your current state, and you just add them up. You want to maximize the sum of additive rewards. That may or may not be true, right? Imagine you want to navigate a car in a particular path, right? It's like a non-Markovian reward function. And that kind of changes the problem, right? And so rewards are additive, that's an assumption. The second assumption is that we're going to assume access to sampling from the dynamics of your system, right? So we're going to assume that you have either a simulator or the real world where you can sample, but you don't know the functional form, right? So as in, I can, there's a black box, I stick some state and action in there, it gives me a new state, but I don't assume I have access to gradients. I don't assume I have access to any functional form of that dynamics. This doesn't have to be true, right? Like often if you have the functional form of the dynamics, it makes your problem in your life way easier. So I'd encourage you to think about, this is a nice framework to think about, but if your problem affords structure that gives you two, then just use it, right? Why not? So that's the second assumption. And the third assumption is that rewards appear magically. And so the environment is going to magically give you rewards as soon as you're acting in the environment, right? So you're in this agent environment loop, you observe state, take action. The environment is assumed to give you the next state and rewards. If you look at any like RL code base, you'll have a step function. The step function takes in an action, gives you a next state, a reward, and a termination position. Good problem does have like if you do something about the problem, yeah, that's a great question. I don't know if there's any like recipe that always works, but like for instance, if you knew something about the dynamics, right? You could like we're going to discuss zeroth order methods, things that don't take the gradients of the dynamics. You could try and do things that do take the gradients of the dynamics, and then that like so you could like change your method from a zeroth order method to a first order method, which uses the gradients of the dynamics. That will like massively lower your sample. You did right. So like there's a whole field of differentiable reinforcement learning, which tries to do like grading through the dynamics. That's like one way of using. Okay. The other assumption that is often made is that you have access to an initial state distribution, and you can reset to it. So you can like essentially sample every episode from that initial state distribution. You're in an episodic set. But if you think about a robot just deployed in the world, you're not really in an episodic setting. You don't reset the world magically. So that's like a research question that I've looked at, and some other folks have looked at. How do we get rid of that episodic assumption? But for the sake of discussion, let's assume that every episode starts by sampling an initial state from some initial state distribution, and then you act according to a policy and according to the transition dynamics in game plan. Yes. So each sample yes. 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 So you're going to assume you have access to a distribution from which you can sample it. So you're not going to assume that you reset to the same initial state. You're going to assume that you sample from initial state distribution. So that's already the assumption. Okay. Any questions about the assumptions before we keep going? Okay, great. So this is remind me of your name. As I was saying, how do we use structure in the problem, right? And so so often in optimal control, you will assume that you have F, you know the functional form of F. And so the optimal control problem is very similar to the RL problem. They're just like these cosmetic differences, right? Like cost versus reward and speed versus continuous time. But I think the main difference that you want to, use is whether like optimal control will assume that you know things about the model, like you assume the functional form of the model, you assume gradients of the model, whereas typically in RL you don't assume that, right? And so it's one way of thinking about it is that optimal control is a much better optimizer, but RL is much more broadly at the cost of being a crappy optimizer. And so it's not magic sauce, it's just changing the assumption. Okay, so so we want to maximize this objective. Maximize acceptance of the work. How do we do it? What are ideas? Great in a sense. Great. Perfect. What are other ideas? Is that the only way? It's great in the sense the one true, the Lisan al-Gaib is great in the sense. Yeah, go ahead. Bayesian optimization. Yeah, definitely. Yeah, so Bayesian optimization is very similar to reinforcement learning. It's a zeroth order optimization, but it maintains uncertainty. But yeah, that's a great idea. Yeah, go ahead.
It's not like way too simple, but if you have a very low state, you just sample everything and create a table.
Sample everything, create a table. So like Monte Carlo, and then discretize your state space and action space, but that may not work in high dimensional spaces. The second idea we're going to discuss is dynamic programming. And so this is like Q learning and soft actor critic and AlphaGo, like all of these are dynamic programming methods. And so we'll talk about dynamic programming. And the third type of method we're going to talk about is model-based optimization. And model-based optimization is saying, rather than directly optimizing something where the functional form is unknown, we're going to approximate something where the functional form is known, and then use that to like optimize through a surrogate model. Right? And so those are three types of methods we're going to cover today. If there's a different type of method we should cover, let me know if we've added it. But this covers like pretty much a large spectrum of RL methods that are used in practice, right? And so let's start with gradient descent, and that's what we'll kind of talk about. Yeah. So let's kind of lay out our outline for today. We're going to start by deriving the policy grid. Not very complicated, but it's just to like get the details right. Then we talk about what makes the policy grid challenging, why it's not just like the solution immediately. And then we'll talk about so we'll talk about what makes the policy grid challenging in terms of variance, right? So we're going to say the policy grid is not immediately practical in all settings. And then lastly, we'll talk about how the policy gradient, when you apply it with deep neural networks, is particularly sensitive to parameterization. And so we'll discuss small changes that make it a little better. Right? Okay, so let's get started. So how familiar is everyone with gradient descent? Yeah, so we'll go over it real briefly. But gradient descent is just, you have some objective function that's called J, right? You're trying to like ascend on J to find the maximum. And so you're just trying to say, move the parameters in the direction of the gradient of your objectives. And so you have your initial parameters, you compute the gradient, you move your parameters in the direction of the gradient till you reach the top of this hill. Right? And so for convex objectives, it'll give you something good. For non-convex objectives, it'll give you something that's locally optimal. Right? And so there's lots of theory on this, right? And why it's good in certain settings and why it's not. But in most machine learning, it's like, or most modern deep learning, it's often very effective, right? The gradient descent is just simply this. You need to know how to compute the gradient of your J or of your objective. And a lot of what we'll talk about today is how to compute that gradient of that objective. It's a little bit different. We'll also discuss a little bit later how gradient descent can be derived as steepest ascent. So it's like the steepest direction for ascent when you put a Euclidean norm on the parameters. So it's saying that if the parameters have to stay within the Euclidean bulk, right, which means that your parameters don't change more than epsilon in Euclidean distance, then the gradient is the direction of steepest ascent. Right? And that'll be important later when we talk about how in deep neural networks sometimes you're very sensitive to parameterization. Okay. So this is simple gradient descent. Let's kind of go through what gradient descent looks like for supervised learning. And so we talked about all of this imitation learning stuff and how it's great, but we didn't really talk about deriving the gradient. We kind of said that was just going to happen magically through PyTorch, right? But let's just discuss it a little bit because it'll motivate why policy gradient is not trivial. So we want to apply gradient descent, right? So we want to compute this gradient. Does anyone have a simple expression for this gradient? Like, what does it look like? You just want to compute this. You want to compute a gradient of this expectation under the log probabilities. For example, S star, A star probabilities. Like, I want to express it in a simple form. I can evaluate rapidly and compute rapidly. How would I? Is my question like that? Okay. So my question is basically, you have this objective, which is the expectation of the log probability of phi data, right? When you're sampling S star and A star from a data set. Let's say, going back to our previous lecture, your data set D is coming from your expert, right? This is just matching likely from your expert. And now I want to take the gradient of that expected, like, maximum likelihood objective with respect to the parameters of your policy field. And I want to compute this. I want to compute this in a form that I can put into code. Right now, this gradient doesn't look like something I can put into code, right? So how do we convert this objective into something I can put into code?
I guess you can first put in the gradient, according to the side expectation, because expectation is linear.
Right. Perfect. So expectation is linear, but I think importantly, this expectation doesn't depend on theta, right? So like there's nothing in this expectation that depends on theta. And so we'll just work out exactly what it looks like. Right? And so let's start by thinking about what is an expectation, right? So an expectation is saying, let's say the expert data set came from some distribution P, right? P of S star A star. You can write out an expectation as the integral P of S star A star of log phi theta, A star given. Right? And so that's just the definition. All I've done is expand the definition of the expectation. And now under continuity assumptions, you can switch this gradient and this integral, right? So you can move the gradient inside the integral when things are continuous. But the important thing is that P of S star and A star does not depend on theta, which means that the constant with respect to theta, right? Which means this gradient theta just has to hit log phi theta, right? Which means you can move it all the way inside to log phi theta. So all we've done is we've taken the gradient of the expectation, right? And we've said that now it's going to be, you've expanded the expectation. You've said that P of S star A star is constant with respect to theta. And now you move the theta all the way inside, so that you take the gradient of the log phi theta. That's the only thing that depends on theta, right? Because you're saying that the data came from the expert, it doesn't depend on theta. So all we've done here is we have taken this expectation, we've expanded out into this integral, right? And we've just said, hey, I'm just going to move this inside to the thing that depends on theta. right? And why is this important? Well, now this thing looks like an expectation again, right? So now you have an expectation, just have a different thing, you have the expectation of the gradient, right? And so now you can rewrite that as expectation of S star, A star from your data set of grad log phi. Right, so all you, this is what you call stochastic gradient descent, right? So all you've done is you've said, I can take my gradient of my expectation, and because the term that the expectation is taken with respect to does not depend on theta, it's just equivalent to the expectation of the gradient. Right? And so this is like when you compute things in PyTorch, right? You just sample a batch, you compute the gradient, you average the batch of gradients, right? That's literally just this. But it's important because when you derive this, you can like skip over this p because it doesn't depend on p. Right? So the way you derive, like the way you like implicitly do things when you're doing things in PyTorch is you're already assuming the fact that your data distribution doesn't depend on your parameters. And that's going to be important because in reinforcement learning it does. That's going to change our objective. Does that parse? It's important. It's a little simple, but it is important because it's going to change the way we do things. Any questions? So all that I've said so far is gradient of expectation is equal to expectation of gradient when the expectation is respect to something that is not dependent on it. Right? This is just standard stochastic gradients. Yes, anyone with me? Cool. All right, so let's keep going. Now, we want to do this for RL, right? So RL says, unlike supervised learning, right? So let's write out the objective for supervised learning, right? The objective for supervised learning is that you're going to sample S star and A star from your data set. And you're going to do log phi theta of A star given S star, right? And so this did not depend on theta. No dependence on theta. In RL, this does depend on theta, right? And so that's going to change the way you do things. And importantly, notice that this doesn't depend on theta, right? So the thing inside the expectation does not depend on theta. The thing that you're taking expectation with respect to depends on theta. And so that's going to change our objective. So imagine we did the same trick we did in the last slide, right? So we expanded the expectations, we moved the theta inside, right? But now the thing you're taking expectation with respect to depends on theta. So you can't just treat it as a constant. And so we're going to work out why that doesn't give you the same objective. But conceptually, the main thing to remember is that in RL, your expectation is respect to theta. In supervised learning, it's not with respect. Okay, so what we're going to try and compute abstractly is this thing we're going to call reinforce, right? Which is basically saying when you have an expectation of x with respect to p theta of x or some f of x, right? That looks like RL, whereas supervised learning looks a little bit different, right? So here we're saying we have the expectation with respect to something that depends on theta of some f. We'll map this to RL in a second. And in the second one, we're saying we have the expectation with respect to something that does not depend on theta of an f theta that does depend. And so that's kind of the difference between supervised learning and RL. And so as we just discussed in the previous slide, in this setting, if this expectation doesn't depend on theta, just move theta inside, right? Which means you have expectation of gradient. So this bottom objective becomes, this bottom objective becomes expectation x from g of x of grad theta f theta of x. Yes, that's the bottom expectation. Well, that's the bottom expectation. And so the top expectation, right? If we try to do the same thing, we say, okay, this is our objective, right? And we try to take the gradient. So we say grad theta integral p theta tau r tau d tau, right? You move the gradient inside, right? Now, if you move the gradient inside, you get grad theta p theta tau r tau d tau, right? Same math, you just move it inside. But the important thing now is that this thing is not an expectation. It's not an app. Like expectations are some probability distribution times some integral over that. There's now a gradient of a probability distribution, not a probability distribution. So this is not an expectation. And if things are not expectations, they become hard to practically. And so integrals are bad, expectations are good. Right? This is just a rule of life. And so as soon as you can convert these to expectations, life will become better. And so The tricky part about RL is when you have the probability distribution depending on theta, the gradient is not an expectation. And so the gradient is not, so the nice part about expectations is you can use this idea called Monte Carlo approximation, just like sample, right? And so anytime you have like an expectation, you can approximate it with samples. When you have something that's an integral, that's much harder to do with samples. And so what we're going to try and do is convert this gradient that's not an expectation into something that is an expectation. Yes. Good.
So you can move the gradient of the integral, but then it loses track of it because it's not an expectation anymore.
It's not an expectation, right? So it's still an integral. You can compute this if you were able to sample, if you're able to integrate over all the trajectories in the world, right? But that's like a huge space for a continuous state machine. Now, if I could convert it into an integral, into an expectation, then I could just sample from that distribution, take an average of those samples, right? And so whenever you have like any of these RL objectives, you really want to get something that's an expectation because you can construct an estimator there and estimate it with samples. Whereas when you have an integral, you have to do it over all the samples.
You're not doing estimation by example points, things like that.
It's biased, though, right? It like only makes sense if you have infinite samples. Like you want an estimator that is unbiased, as in it'll get, you know, in expectation, it gives you the right objective. Okay, so what we're going to try and do here is we're going to try and approach objectives that look like RL. So things like this. Specifically, we're going to look at this objective, right? We're going to try and force it into, we're going to force the gradient of that objective into something that looks like an expectation, right? That's our goal. And when it looks like an expectation, I can implement it in PyTorch. I can do all the like nice stuff that I want. Right. So the important thing is that the gradient is with respect to the expectation variable, not the thing that's inside it. That's what's going to make it tricky. Now, you know, Sam was talking about something if you had structure, right? So if you knew the structure of p theta in a particular way, there's a trick you can use called the reparameterization trick, which allows you to move all of the theta stuff inside and compute a lower variance estimate. We're not going to cover that today, but it's a good thing to know, and I'll cover it in the later session. Okay, so, okay, we ready to derive the policy again and feel good about it? Does the problem make sense? Or does it seem trivial? Okay, good. Okay, so what we really want to do is take this objective, right, and compute its gradient. Now, for the sake of like notation, and so that we just don't spill over the whole slide, we're gonna try and denote this as in its trajectory view, right? So you can think of this as, you remember from our discussion in our first lecture, you can write this as trajectory. You can write it as an expectation over a trajectory of a reward of the trajectory, right? Where a trajectory is a sequence of states and actions. Right, so the objective above is the same thing as this objective, just in shorthand. So you can think of a trajectory as a sequence of states, actions, rewards, states, actions, rewards, states, actions, rewards. And you can think of the expected reward as the likelihood of the trajectory times the reward of the trajectory integrated over. So that's the expected reward in the trajectory view. And the trajectory depends on theta because your actions that you sample depend on theta, right? And so your trajectory depends on theta, which means that unlike your policy, your actions are going to be determined by your policy. So theta is going to determine your whole trajectory. So the likelihood of the trajectory is critically dependent on theta. So it's the same thing that we talked about last time, or in the last slide, right? We're just going to have p theta tau and r tau integrated over theta. Okay, sweet. So we want to do the trajectory view. And so now you guys are going to walk me through this, right? So we're going to try and compute grad theta, j theta. What's it going to be? We're going to say grad theta integral d theta tau, r tau, d tau, right? So what's next? Switcheroo. And so you switch it in. This gives you integral grad theta p theta tau, r tau, d tau. Right? Okay, so now I want to make it into an expectation. Okay? What's the magic sauce? Well, so just a reminder, expectations are of the form, you know, something like that, right? Which is integral px fx dx, right? So I want to have a probability multiplied by some function and take integral over everything, right? So this is almost there, but there's no probability in there, right? So how do I How do I massage this into an multiply and divide by p theta, right? Perfect. So you say you have p theta tau, right? And you do grad theta, p theta tau, r tau, theta. Okay. So this is great because now what you can do is you can like think of this whole thing as like f essentially, and then this is your expectation thingy. That's great, right? So okay, so that is good. Now, but we want this kind of nasty little thing to divide by p. Don't know p. Yeah. And so how do I simplify this?
Gradient of one.
Gradient of log. It's like you've already seen my lecture. So this is perfect because basically if you take gradient theta of log p theta, you can write this as just by chain rule, right? So the chain rule of probability says this is 1 over p theta of tau times, the gradient with respect to theta of p theta of tau, right? So this is equal to this just by chain rule, which means you can just like replace this whole thing, at least, sorry, this thingy here, you can replace by grad theta log p theta. Sorry, what?
Are you writing off the screen?
Oh, sorry. Oh, I should move up a little bit. Yeah. Okay. So, wait, I got cut off a little bit. Yeah. So, yeah, let's see if I can. So I guess my point here is that I can just go back to my typesetting. But basically what we've done is we've moved the gradient inside. We multiplied and divided by p, right? And then we've said that by chain rule of probability, the gradient with respect to theta is good. You could rewrite this term grad theta p theta tau by p theta tau as grad theta log p theta tau, right? Just by chain rule. The chain rule says if you take the gradient log p theta tau, let's just rederive this real quick. So grad theta log p theta tau is equal to 1 over p theta tau times grad theta p theta tau. Let's just chain. Yeah, go ahead. Yes. Well, it's infinitesimal, right? So it's like in practice, you just like add a little epsilon. It's not collapse, right? But when you like simplify, like often, like the way that division by 0 will reflect is that this log probability will like explode, right? And so typically in practice, what you will do is you like flip it, or you like do things, or add an epsilon to it, so you prevent that kind of blow. Good question. Okay, so what we've done here, like why is this important, right? What we've done here is we've taken our thing that wasn't an expectation, and we've converted into a thing that is an expectation, right? So this is an expectation because it's a p and something that looks like an f, right? So let's call this f, let's call this p, and so now you have integral p times f, which is an expectation, right? And so the nice part about the way we've written this right now is that it's an expectation, which means I can rewrite it as the expectation p theta tau grad theta log p theta tau r tau. Okay. So I've reconverted into something just like I did for supervised learning, right? Supervised learning is way easier because we said it's just going to be take the gradient of every log probability and average them all. What we've done here is we've converted the gradient of the RL objective into something you can take the expectation of. Or expectation of. Does that make sense?
Maybe it's on the patient thing, but here is it's over p theta tau.
Oh, it's just saying that trajectories are sampled from. Okay. Yeah, so that would be tau, sig, tau, whatever, yeah, sampled from.
Get from the rollout.
Yeah, exactly. You sample it from the row. So this is still a little abstract. The next slide, we're gonna reduce it back into states and actions and PyTorchable things, right? So anytime that I'm giving you abstract things that are not grounded in PyTorchable things, you call me out and we'll make it implementable, right? Okay. So the point here is what like the only thing we've really done here is we've taken gradient of the thing, we've made it into something we can take a spatial spectrum, which means we can evaluate it with samples. Right. Now let's try and go one step further and go from the trajectory view back to the state and action view so we can actually implement this. And it'll be clear why this is called model-free reinforcement learning and why this is nice and simple, right? Yeah.
Is this reason for multiplying dividing by data tau apart from the log trick? Don't have to use any other like you did the sample probability.
That's a great question. So right now we're just using the on policy distribution. So using p theta tau, which is equal to like the same thing as your policy. You can also do off policy gain where you can multiply and divide by different q. And that is nice because you can use different data distributions, but that is like a little more complicated because your importance weights will grow. Let me see if I can squeeze that in next lecture. It's a fun thing to look at. Okay. So this is often called the reinforced trick, right? And it's not just applicable to reinforcement learning, it's applicable to any black box optimization. Anytime you have a problem of the form, anytime you have a problem that we discussed in the last slide, anytime you have a problem of this form, right? Where you say you have a function that evaluates your thing, you don't want to compute gradients through it, right? And you want to do this 0th order, that you don't want to compute gradients through f, right? You can always use the same multiply, divide by d theta trick, right? So anytime you have black box optimization, you can do it with this reinforced trick. So the important thing to note is when you go to our expression here, the figure expectation of is r with respect to d theta tau, but you're never computing the gradient of r, right? So the reason it's useful for black box optimization is because you never compute the gradient of r, you just compute the gradient of log p theta tau, which is under your control. And so anytime you have any optimization, which is a black box, imagine you had, like, for those of you who are interested in code and those kinds of things, anytime you have something that's non-differentiable, right? You can kind of skip over it using this trick. Because this trick just needs you to take samples. It doesn't actually need you to take gradients through that non-differentiable thing. Right? So yeah, think about it as a general idea for black box optimization, which is really useful for RL because you don't assume functional form of the gradient, functional form of the dynamics, right? So you don't know the dynamics, which means you can't take the gradient through them, which is going to make it tricky, right? Now, but if you don't know the dynamics, so how do I compute this gradient, right? I said this is the likelihood of a trajectory. A trajectory includes all of these like steps, and the dynamics are in there, right? So like, how do I compute that? Seems like an intractable thing. And so what we're going to do next is we're going to try and show how that's tractable and how it's model free, right? Okay, before we go further, a lot of math. Any questions? This is crystal clear.
I have a question.
Yes.
So what's the downside of this then? Because it seems like you just made it extractable with no like.
It seems like magic. Yeah. So the downside is that you're not using any structure of your problem, right? So you're saying that I have this f. Like you can almost think of policy gradient as like trial and error, right? So it says that imagine you have a black box function f, and you're just like sampling a bunch of stuff and choosing the better stuff more and the worst stuff less, right? That's it. Like that's, you can, if you look back at let's write out the objective, right? So if you go back to the previous slide, right, you can think of this intuitively as saying you sample trajectories, right? You say things that have higher R, you increase the log likelihood. Things that have lower R, you decrease the log likelihood. So it's like, imagine you're throwing a bunch of darts at a dartboard, and things that are good, you do more, things that are bad, you do less. And so if you're using less of your problem structure, which you're going to be less efficient, right? And so essentially you're using none of your problem structure as completely black box, which is what makes it so inefficient, which is why like we hear people say PPO is so inefficient and not sample efficient enough, and blah, blah, blah. Because it isn't, right? Because you're just doing black box optimization. And that's a trade-off. Like when you use the gradient and use structure of the problem, then you can it tells you which way to go. Otherwise you just sample it.
So your sampling can make it better. This sounds very similar to like Markov chain month pro, like you just do a bunch of random stuff and see what sticks.
Yeah, it's very similar. Okay. So it's important to see that it's policy gradient with respect to, not with respect to the reward. Policy gradient with respect to the parameters of the policy. And so it's not gradient through the dynamics, not gradient through the reward, it's gradient through the parameters of the policy. And so let me go to the next slide, and these things will become a little more clear when I write in full objective, right? So what we're going to do next is we're going to try and take this objective down here, expectation p theta tau, grad log p theta r tau and like implement it in a form that like is states, actions, and policies and grounded, right? So what you want to remember is that by our logic of trajectories coming from ancestral sampling, right? So you sample an initial state, then you sample an initial action, then you sample the next state, and you sample the next action, right? You just sample things in sequence. So if you remember our chain, we started at S0, we sampled A0, then we went to S1, sample A1. Right? So you can represent the likelihood of a trajectory, p theta tau, as the likelihood of the initial state, p of S0, times the likelihood of the action A0 given S0 times the likelihood of the next transition, p of S1 given S0 A0. You can repeat this over and over, right? So let's write this out. You can write out the trajectory as p of S0, initial state, times pi of A0 given S0, initial action, times p of S1 given S0 A0, initial transition, right? And then you repeat. So you say pi of A1 given S1, p of S2 given S1 A1, repeat, right? So to get the likelihood of a trajectory, you just take the likelihood of the initial state, multiply by the likelihood of the initial action, multiply the likelihood of the initial transition, and yeah.
So you have to use like a.
Yes, so the Markov assumption. Yeah. Yes, like at least most of the things we'll discuss are going to be Markovian, although the policy gradient you can actually derive without the Markovian assumption. Just like a little more involved, but you can derive the whole policy gradient without the Markovian. But other algorithms we'll discuss, like Q-learning or model-based RL, are typically Markovian. It's a great question. Okay, so what we've said is our likelihood of a trajectory is going to be likelihood of the initial state times the product of the likelihood of the transition times the policy from the first step to the last step. Okay, that's going to give us the likelihood of our entire trajectory. Yeah. So now what we want to do is we want to take our previous objective, right, on the last slide, and we want to convert it into something grounded. So we're just going to stick in our definition of p theta tau into that objective, right? So our objective had log p theta tau. Right, so log p theta tau, just log of a bunch of products is sum of logs. So you can write this as log p of the initial state plus sum of log p transition plus log pi of the action. Right? We just like took log of this product of a bunch of stuff. So all we've done here, p theta tau defined by an ancestral sampling, log p theta tau is just sum of all of these terms. Okay, so the next thing we want to do is take the grad log p theta tau, right? So if you remember our policy gradient objective, it's expectation of grad log p theta tau r tau, right? And so we just want to take the gradient of this. And so gradient of a sum of things is the sum of the gradients, right? So you can say it's sum of the gradient of the initial plus sum of the gradient of the dynamics plus sum of the gradient of the policy. Now, can we like set some of these terms to 0? Which ones? The first two, right? The first two are not dependent on theta. Theta is purely a policy thing, right? The dynamics doesn't depend on theta. The initial state doesn't depend on theta, right? So this is the only thing that depends on theta. Nothing else depends on theta, right? And so this is going to be great because we can just cut them out, right? And so the nice thing about cutting them out is that it becomes model free. Right? So when I say something is model free, I don't actually need to know the gradients for the dynamics. I just need to know the gradients for the policy. Right? And the gradients for the policy, let's say you chose your policy to be a neural net, it's just backprops for your own neural net, right? But you don't need to know the gradient of the environment, which is what makes it perhaps easier to use than some optimal control methods, because you are going model free. The trade-off is that when you're model free, you're more inefficient, as Varun was just talking. So, okay, so let's recap what we did here. We started from our RL objective. We want to take the gradient of this RL objective. We want to convert it to an expectation. Okay? So we convert to the expectation under p theta tau of grad theta log p theta tau times r tau. That's the first step we did. Main trick: multiply, divide by p theta. Use the chain rule. That's it. Okay? I use this trick everywhere. It's great. Second thing we did is we just defined p theta tau with ancestral sampling. And we said this is going to be a sum of these different terms with initial state distribution, transition dynamics, and your policy, right? And then we said two of those terms actually don't depend on theta, and so you're completely model free, right? And then what this allows us to do, it says that grad theta log p theta tau is just the sum from 0 to the end of grad theta log pi theta at given s, right? And this is completely computable with auto differentiation because pi theta is something you completely control. It's your policy, right? So all you need to do is stick in your state into pi theta, get your action, and do torch dot backwards. Right?
Sounds like back to policy. Essentially, because the policy is a drug.
Yes.
So are you gonna map states to action?
How are you going to map state to action?
Because state can be an action.
So that's the whole magic of function approximation, right? So you're like, neural net is going to take in, like, let's say it's a neural net, right? You're going to take in like a vector of your states. It's not a table, it's a vector of your states. Go in, you pick it through your layers, and out comes the distribution over action, the continuous distribution. So we talked about invitational, we talked about Gaussian, we talked about mixtures of Gaussian. You can use any of those forms for pi theta, but essentially you have something that can take in an input in, let's say, Rk, which is the state space, and then output is a distribution over Rm, which is the action space. Right? And so that's going to be your neural net. You just need to take a gradient backwards through it.
Maybe you'll get those, but like gradient with respect to like what laws, because I don't see any notion of rewards baked in.
We're going to get back to it in the next slide. That's great. Yeah. So all we've done here is we've written what grad theta log p theta tau is, and our loss is what we defined in the previous slide, right? We said that this is our objective, our overall objective. We convert it into this piece. This is our overall gradient, right? And now we're just going to like take what we did on the next slide, put it together with this to get a complete objective. So let's just go through that, and then we'll try to understand the intuition and kind of unpack it a little bit after. Okay, so we've shown that grad theta log p theta tau is the sum of grad theta log pi theta at every single time step, right? And so now what we can do is we can take our initial objective, which is saying you have expectation of trajectory sample for p theta tau. But here this notation is perhaps a little more amenable, right? And then you take expectation of grad theta log p theta tau times the sum of rewards in the trajectory, right? So that's what we call R tau. So grad theta log p theta tau R tau, taken an expectation over trajectory sample from p theta tau. That's what you derived 2 slides ago. And now we have this like magical expression for grad theta log p theta tau. Let's substitute it, right? So now the gradient you can write as you're going to substitute grad theta log p theta tau, the sum of grad theta log pi theta at given st. The thing we derived in the previous slide. So we showed that grad theta log p theta tau is the sum of gradients at every time. So the gradient of the trajectory with respect to the parameters theta is equal to the sum of the gradient of the policy at every single time step, right? So it's model free. We're just going to stick that into our objective. Now our policy gradient is take the expectation of the trajectory. This is just the long form of the expectation of the trajectory, which says sample in an initial state from P of x naught, sample an initial action from pi of a naught given s naught, sample the next action to sample your trajectory. And then you're going to compute the policy gradient as the sum of time step from 0 to t of grad theta log pi theta at given st of the sum of rewards in the trajectory, right? And so all we did here, so let's just make sure we remember the steps, right? So we started with j theta. We took grad theta j theta and we converted into this form, which is expectationable, right? And then what we did is we took grad theta log p theta tau. We showed it doesn't depend on the gradients of the model. And so we wrote it as this sum of gradients of the policy, right? Sum of gradients of the policy. We just plug that in. And now we have something which is like fully grounded in terms of states and actions. So the gradient of your objective, or into your question here, the gradient of your objective is you take trajectories sample from your environment, and then you just compute this gradient by say taking sum of grad log pi, multiplying it times your sum of rewards, and that's going to be your overall gradient to move your parameters. So this still is not in terms of something we can take samples with respect to, but because it's an expectation, right? You can, whenever you have an expectation, you can replace it with this Monte Carlo approximation. So let's say you have an expectation of some, P of X, F of X, right? You can always approximate it with some 1 over N sum of F of Xi, where Xi is sampled from P of X, right? So you can say that whenever you have an expectation, you can just take a bunch of samples from that distribution and then just like average that to the expectation. And so now we can take our thing, which is an expectation, and now just approximate them with samples. We say, let's say N samples. For each of the samples, you're going to distribute grad log phi multiplied by sum of rewards. That's going to give you your whole gradient for a policy. And so what does all of this mean? This means I have my RL objective and I've computed a gradient to move my parameters in so that I can maximize my RL objective, right? So once I have grad theta j theta, I just like move my parameters in the direction of the gradient that maximizes or my expected reward. Okay. Yes.
If you approximate the policy in your network,
Yeah.
and use Gaussian distribution, the output of your network will be like mean and variance.
Yes. So the output will be mean and variance. And so then this log probability, so it's like, let's say we did a Gaussian, right? So log probability will be something like X of, 80 minus mu of ST by sigma of ST squared or something like that, right? And then so you take log of this thing, right? Which is just going to give you minus 80 minus mu of ST by sigma of ST squared, right? And then you're going to take the gradient of this. Let's call this mu is going to be a neural. Technical difficulties. Okay, so this is going to be mu of ST squared. Let's say this depends on theta. Let's say mean, like you have a neural net which takes an S and gives you the mean, and S and gives you the variance. And you're going to take gradients with respect to the parameters of that neural net. Right? And so you're going to take gradient of this with respect to theta, right? Something like that. Okay. So, all right. So this is kind of our overall objective, which is going to be our Monte Carlo approximation, right? Yeah, go ahead. Why use Gaussian? It doesn't have to be Gaussian. Gaussian is a choice. Right? Like you can use any policy distribution where you can evaluate the log probability or the grad log probability, right? You can use any of those. Gaussian is a particularly easy choice because it's like what I
So it's the reward function, just the reward function, does it ever change?
Yeah, so the RL, like if you're like gradient descent needs to have a fixed objective, right? Otherwise, it has no guarantees. Like you can't change your objective in between. And so we're just gonna assume that R is a fixed objective. Now, this doesn't always hold in practice. Like for instance, in RLHF, right? Often you're like training your reward function as you're training your policy, and sometimes those things change, and then the guarantees don't hold anymore. But what we're going to do here is we're going to assume that R is a fixed function. And it does, we're not taking grades to it. So it could be arbitrary, it could be non-differentiable, it could be a step function, it could be an indicator, it could be a human label. Any of those things are possible.
So I'm trying to understand how like the sum of the rewards relates to some of these ones. So let's say, I do a roll up, I sum up the rewards for all the time steps for this trajectory. Is that final reward multiplied times the gradient for each of the steps, like the same reward?
Yeah. So you're going to say, take a trajectory. You're going to sum up the rewards for the entire trajectory. Yeah. And then you're going to say, take the grad log prop for every single thing in that trajectory and multiply them all by the same sum of rewards. So take an entire trajectory, each of them has a grad log prop at every different time step, and multiply the same sum of rewards to all terms there, and then sum them. And that's not going to be great.
Yeah.
We're going to make that better.
Okay.
But the reason to do that is because you need to like your policy doesn't just determine your current time step, it determines everything in this. Right, so you can't ignore everything else in your time step. Or in your future, we'll show that you don't need to depend on things in your past, but you definitely need to depend on everything in your future, right? Because your actions are going to determine your next states, which are going to determine your next state. So your policy has a long-term dependence. Okay. Yeah. Go ahead.
If we use discounted rewards version,
Oh, discounted rewards, you're going to stick them in right here. So discounted rewards would be gamma to the DR over here. And so it's gonna be grad log 5, the same thing as
Still a sum of everything.
yeah, still the sum of everything. But the nice part about discount is that it like kind of like things way in the future don't affect your reward too much, right? Because they're discounted. And so it like lowers the variance of your estimator because it like doesn't affect the reward. That's the nice part. Like you can think about discounting in policy grade as essentially reducing variance. Right, so we'll talk about why variance and all these things in a second, but it's just jumping ahead, that's what this matters. Okay, I want to take 2 minutes because we did a bunch of math and just like everyone to decompress for a second, and then we'll get into why this is a pain. Right. Okay, go ahead. Thanks. So yeah, reconvene in 3 minutes. No, but now they're your papers.
Very good question.
Yes.
Why is the key becomes of keys that are optimized like very good slide? Just make university. Yeah. Same with the slide.
D minus, oh, like the top thing?
Yeah.
So this one?
That's a typo. That's one.
Yeah, that's a typo. Give me 1 sec. So you're just gonna sample, you're not gonna sample the last time, you're still gonna have the gradient at the last time step. Actually, the difference goes to the last time step because there's no sum of the part. No, you have one time step. So like, the way that should actually work, right, is that if you look at your objective here, right? The last time step, right, like, you still have like, you still have the last time step. Yeah, because at least the easy thing is the worst of them. Especially if your reward depends on then your like last time step still matters because it determines the action. What's up?
Two questions. One
Yes.
personal, one math related.
Okay.
The first one is so on the 25th.
Uh-huh.
Scheduled surgery and it's I'm gonna be out for an indeterminate period of time.
Okay,
Can I get some leeway on?
of course, of course,
Yeah, I guess my question is like, I don't know what the kudo thing is, because some of the teachers would like me to tell me how many days are gonna be gone.
Do your thing, don't worry.
I appreciate that.
Yeah, and as you probably figured, I'm very loose with
Thank you.
grading, and so you need more time for the homework, absolutely, you can skip the homework, it's fine. The goal is not to like make your life hard, because yeah, take your time, and things will be recorded to watch that as a program.
I really appreciate that. Yes. My question is, just really quick, maybe right on. Why did you keep it?
Oh, yeah, because it's things that work. I guess in this case, what you're saying is you're gonna like, don't say like you think bracket here. Imagine you were at somewhere right around 0, right? You're still gonna sub over all of the.
Okay, so like for equal, you calculate this first.
Yeah.
And apply it to T equals 1, 2.
And what we talk about next is why that is not great. And then primary important for the but when you can look at it like this, there's a large bracket and this is a large bracket.
To try to estimate the expectations. You'll have things that's like log trade. Like on the previous slide, you had instead like estimate the angle by sampling. So is this like term right here, like a factor of which should be biased?
The factor by which it will be biased. I guess it depends on your sampling distribution, for example. Okay, and so like imagine you sample from the uniform, then your like bias factor would be some like E theta by P. Yeah, because the policy, it's really under your control. The strategy of how
Yeah. I get why not? Like down, so I don't feel like or yeah. And so that's why you elevate the more. Didn't think about this. Yeah, exactly. I'm studying this. I like that.
All right, so we get back to it. Okay, so we talked about the RL objective, we talked about how we can approximate it with this expectation, right? So we said we can approximate it with samples using this expectation, using our Monte Carlo approximation. That's nice because it's something you can implement, right? But what does it mean? Like, what is the intuition here, right? So all that RL is doing is it's saying, let's sample a bunch of trajectories and let's increase the likelihood of the actions which are in the higher term trajectories, right? So you can almost think of it like, hey, we're just like sampling a bunch of stuff. The good stuff you do more of, the bad stuff you do less of, right? And so if you kind of view it in this trajectory form, you're saying, let's sample a bunch of trajectories. Some have reward 30, some have reward -10, some have reward 100. Things in the reward 100 trajectory, you do more of. Things in the reward -10 trajectory, you do less of, right? So all your, it's like just formalizing the notion of trial and error, saying do a bunch of trials, things that are bad, do less, things that are good, do more. That's all that it's doing. So the way to kind of intuitively see that is it's saying that like, you can think of grad log prob as like increasing the likelihood, and you're increasing the likelihood weighted by the sum of rewards, right? And so you're just saying, do stuff, increase the stuff that has high reward, decrease the stuff that has low reward, right? So negative reward, you can think of as like pushing down, positive reward, you can think of it as pushing up, right? And so that's just the easiest way to think about it. So that's intuition. It doesn't all, the rewards like don't always have to be positive or negative, but that's the easiest way. But yeah, all it's doing is formalizing trial and error. It's not taking the gradients to the rewards. It's not taking the gradients to the dynamics. It's just saying sample a bunch of stuff and do weighted. You can almost, if you remember what imitation learning was, it is this objective without the R's, right? They're just saying like maximize likelihood. Right? So it's saying that you had perfect AP, you had perfect ST, just maximize likelihood, right? And then it's great because the data was perfect. You want to replicate it. But in RL, the data can be arbitrarily bad. So it's like, you can almost think of it as weighted maximum likelihood. So say, sample a bunch of stuff and then do weighted maximum. So just like, in a way, you can think of it as like filtering out the stuff that is bad, keeping the stuff that is good, proportional to how good it is. And that's the easiest way to do it, right? And so that's how we're gonna kind of implement it, right? So you're just gonna iterate in this loop of collecting data, taking a gradient step, collecting more data, taking gradient step, repeat, right? And each time you take a gradient step, your gradient step is gonna look something like this, right? Where that grad theta j theta term is gonna be this thing we've defined up in the right? So you can compute the gradient up in the right. And every time you wanna implement the algorithm, you're gonna say sample a bunch of trajectories, compute this gradient, right? And then take a step on your parameters, and then collect more data with your new parameters. Right? And so you iterate in this, it's called an on-policy RL algorithm because you're using your latest batch of data. Right? So it's important that you use your latest batch of data and not arbitrary prior data, because when you're taking this expectation, right? This expectation, sorry. Your expectation is with respect to P theta tau. It's not with respect to arbitrary prior data. It's with respect to your current data distribution, right? So you can't just use arbitrary data. And so you have to be on policy, right? So policy gradient is an on policy algorithm. You're saying, let's sample a bunch of trajectories from the current policy, only the current policy. And then you're just going to take the compute the gradient, move your parameter, repeat. And so it's on policy. What makes that good or bad? Like, what are the trade-offs of being on policy?
Optimization could be slow, it's a reasonable step you have to sample.
Optimization could be slow, could be really data inefficient, right? Because if you're only using your latest batch of data, you have to sample a lot of it, right? And so the reason like Algorithms like PPO or TRPO or vanilla policy grid, I think we described, are slow is because they're on policy. And so you have to sample huge batch sizes. So things like ISIG-GIM and ISIG-SIM make this easier by like letting you parallelize 1,000 times. And so you can sample a huge batch size. And so that's what makes policy gradient kind of inefficient, the fact that it's on policy. And we'll talk about how it's high variance and has other issues. Okay? But the general loop is going to be sample, compute the gradient, move the parameter, sample again. Okay? So if you look at any RL algorithm code base and you're trying to understand it, it's always some version of this loop. Okay. So let's try and understand how it's connected to supervised learning a little more closely, right? Because supervised learning is the only thing that truly works. So we need to connect it back to supervised learning, right? Which is saying that reinforcement learning is essentially weighted supervised learning. And so you can think of it as you're computing your gradient by taking your grad log probabilities and weighting them by the sum of the rewards. So you can think of it as like selecting good data and increasing the likelihood of your selected data. Not quite that discrete, but you're saying good data, do more, bad data, do less. But it's important that in RL, because the like data distribution depends on data, you have to keep resampling. Whereas in supervised learning, you don't have to keep resampling. The data set is fixed, right? And so that kind of changes the calculus a little bit. And the important thing is that in RL, your performance is determined by the things that you sample. Right? Whereas in supervised learning, exploration is not a concern. None of those things are a concern. Basically, if in my trajectories, in my 0 to n trajectories, if I didn't sample something that was informative, then RL is not going to compute a useful gradient. Right? Whereas in supervised learning, that's much less likely to be a problem. It can still be a problem if I have a huge data set, but it's much less likely to be a problem. Does that make sense? The connection between them? Okay, so let's try and get to implementing this. Yes.
Have a soft threshold. Let's say at some point your policy is so bad that the final state is going to be really bad and you're wrong. Slide somewhere.
That's a great question. Often what you'll do is you'll like do it with multiple restarts, or you do like population-based trading where you start a bunch of different things. And then something is like not making progress after a while, you kill it.
No, you just restart where it stops. Or
No, because that is still collecting bad data, right? So you just restart it. Do you like some of the algorithms that we use today, like they try to prevent you getting into such a bad state? Like often what happens when you get into such a bad state is you like venture the really bad part of optimization land where you can't get out of. And so many of the things try to like prevent you from getting there. That's the question. Okay, so how do we implement this, right? If you want to use autodiff, right, you're going to take this objective. You're just going to compute the grad log probability, right? So you're going to use like torch.distributions.gaussian, where you're going to feed in, you're going to have a function S that goes and maps to a mean and variance. You're going to stick it into torch.distributions.gaussian. You're going to take the log likelihood, you're going to take the gradients through that, right? And you're going to multiply that times some sum of rewards. And remember, you're not taking the gradients to the rewards. Rewards are like constants. Right? They're not things in your autodiff graph. So you're just going to use the gradient for the policy. Right? Yeah.
Just on the previous slide, you mentioned sample, like you want to sample good stuff. So aren't you, if we're doing your sample, the first step and the bias can to only take good actions on good state. So how do you sample that way? Like,
You don't know what the good samples are, so that's the challenge of exploration. Right? So you're going to start by like sampling a bunch of stuff. It may not be good. And then you're going to like weight the stuff that is best amongst what you sampled, and then try to sample more around.
when you're assuming that your policy gets better over time. So
Yeah. So like in any grade, it's a local search method, which means that you're like assuming that there's local search will get better always. And so you're still you're saying I sample a bunch of stuff, I go towards the better stuff, and do local search, and the hope is that local search will get you something. Good one. Okay. So all you're going to do is compute the gradients with autodiff, sum of rewards in a trajectory. Usually you don't have to like actually compute this whole objective manually. You can construct a simple, we'll cover the PyTorch code in a second. But you can compute like a very simple surrogate objective, which looks a lot like supervised learning. So you don't have to like actually do all of these summations. But yeah, you don't have to like really do a lot of this yourself. In practice, you can just use torch.distributions to get away with this Gaussian or whatever choice of policy class you want. You can use autodiff to compute this grad log probability with this sum of it. Okay. So let's kind of look at the code a little bit, right, and try to understand what's happening in the code. Don't copy this for your homework, but that'll make my classes a little harder. I give all the homework answers. Okay, but this is maximum likelihood. So what we're doing here is let's say we're in a discrete space for now, right? And so in maximum likelihood, what you're going to say is that this is what we do in invitation learning, right? So you say taken states, your policy, let's say predicts logits, right? So you say if you have a state, let's say you have like 10-dimensional discrete actions, you're going to take in states, you're going to predict a 10-dimensional vector, right? That's going to be your like logits for categorical distribution. If you remember Zoe and Patrick's discussion, it's like this is like what you do with the cross entropy loss, right? So you say you predict the logits, you compute the negative likelihoods using like the cross entropy loss with the labels, right? So the labels are your optimal actions, your logits are your predictions, right? And you can think of maximum likelihood as say compute the softmax cross entropy against those logits, right? You're just trying to say try to maximize the likelihood of the actions that are in your expert data set, right? And then your loss is just going to be the mean of those likelihoods. You're going to try and reduce the negative log likelihood, means you're going to maximize them. So all you're doing is this is your prediction. These are your labels. You're trying to compute negative log likelihood. You're trying to minimize negative log likelihood or maximize likelihood, right? It's 4 lines. Then you take gradient, move your parameters, done. Right? So this is like all of last lecture, the lecture before. You basically do this. So you can replace this with other things for a Gaussian. Like for a Gaussian, this would not be softmax cross entropy. This would be like mean squared error. Right. And so depending on your probability distribution, this law changes. Right. So this is maximum likelihood. Bear with me on how this works. Okay. So all we're going to do in RL is we're going to do exactly the same thing, but we're just going to multiply these negative log likelihoods with some sum of rewards. Let's call them Q values for now, right? You're just going to compute the sum of rewards in the future, like literally in your trajectory. Take your trajectory batches, compute the sum of rewards in every trajectory, right? And then you're just going to multiply the negative log likelihoods by those sum of rewards. And then you're just going to do the same thing. So it's a one-line change between supervised learning and RL. You just take your supervised learning step weighted by the negative log likelihood. Weighted by the sum of rewards. Sorry. Everyone follow that? So all we've done here, don't worry about Q's or anything. All you do is take your trajectories, just run like a sum, right? And then you're just gonna say, I'm gonna multiply the negative log likelihoods by the sum, and that sum, I'm just gonna take the average over all of the trajectories, and then you're done. And then you take the grades of that. Notice that these Q values are things you don't take the grade with respect to, they just weight your grade. Okay, is that like, so the main point I want to get across is it's not that different than supervised learning. It's kind of supervised learning, just weighted. Yeah, anything? Great. Okay, so this seems good, right? All that it's doing is formalizing the notion of trial and error, and you can use it for things that are, sorry. You can use it for things that are like not so trivial. So these are some like algorithms that are derived from similar things. They're not quite the same thing. I don't know if you guys can see it, but there's a humanoid doing stuff. And the important point I want everyone to notice here is if you look at these learning curves, right? This is for Hop Cheetah, which is an extremely easy environment. That's like over 1 million timestamps. So if you have 1 million episodes for, silliest possible tasks, that seems like crazy. And it's like impossible to use in any practical setting. And so, the questions we need to ask with policy grading is how do we make it practical? How do we take this? Like seemingly intuitive conceptual idea and like make it less sample inefficient so that it can become practical for robots or for applications where data is scarce. Okay. So the way we're going to do that is there's some conceptual issues with the policy grade. We're going to try to figure them out. They're going to help us with sample efficiency. They're going to the two issues we're going to talk about is the variance and the parameterization. So let's start by thinking about the variance. So what makes the policy gradient challenging is that it's really hard to tell what matters without many samples. Right? So remind me again,
Arya.
Arya. So what Arya was saying is like, okay, you have to like sample a bunch of stuff. You don't know which stuff is good, right? So in practice, policy gain only works if you have huge batch sizes. You sample a lot of stuff and you see a lot of things, right? And so essentially it becomes hard to tell what matters without many samples. And this is like often formalized as a notion of variance, right? And the primary issue with policy gain is that it's a single sample estimate, right? So what I mean by a single sample estimate is that if you look at this particular trajectory, right? So really this thing is this, right? So what's happening is that you take the grad log probabilities and you're like weighting them by the sum of rewards in just that trajectory, right? So it's a single sample estimate because you're saying that like you're only weighting it by the sum of rewards in that one trajectory. And that one trajectory was just like one chance occurrence that happened in each sample in the environment, right? So like it could have been affected by an unlucky sample. It could have been affected by stochasticities. It could like have done 20 good actions and then one bad action and totally fucked it up, right? So essentially you're weighting your objective by single sample estimate. A single sample estimate is really high variance, as in you need to sample a ton of single sample estimates to get what you want. And so this is the issue of variance that is often described in policy gain. And all of these things are essentially just like symptoms of the problem of variance, right? So for instance, you're coupling together all the actions, right? Which means that, okay, let's say you had A1, A2, A3, A4, and let's say these were like good, and like these, a couple of these were bad, right? Whatever, A6 bad. Now what's happened is that you've taken these good actions, right? You were good until here, but then you were like catastrophically bad in the next set of things. You've taken those like those bad actions, you've coupled their outcomes with the good actions. And so you're really going to downweight A1, A2, and A3 when you didn't really want to downweight, right? And so you're coupling together all the actions. And this is like the problem that often is referred to as credit assignment. So it's hard to assign credit to like, you got a bad trajectory, was it because of this, or this, or this, or this, or this? It's not easy to assign which things are good and which things are bad. Secondly, you're susceptible to scale variation, right? So if you like add and subtract your reward by a different amount, really it shouldn't change. The gradient is a constant, but it like is very susceptible to these scale variations. And it's also susceptible to lucky samples. So like you're sampling in the environment. Let's say you got lucky and like magically had your humanoid go backwards. And it's gonna like take that as possible, even though that might be an extremely lucky sample that's not likely to repeat in a stochastic environment, right? So you don't want to have estimators that are really susceptible to these lucky samples, right? So all of these are like symptoms of variance, and the way to like fix them in policy gain is typically to use like a shit ton of samples, so like make n ginormous.
It's like it's susceptible to scale like the reward.
Yeah.
So say your reward is like a summation of a few distances. What would be the best way to scale that in a way that would perform?
Yeah, so we'll talk about one solution, which is like using something called a baseline, which is essentially trying to center, like always make it zero centered and like divide by some variance. So like normalization you do in supervised learning often, something similar. So that's one thing that people often do. People often like normalize advantages. So like some normalization things are good to do. Yeah, that's the easiest thing.
The reward function, where the curve function learning
It's just magically appears from the environment. Like it's part of the environment definition. So
that's not defined well, then you can just train a model to reward actions.
absolutely, absolutely. But that's true of like any optimization problem here. Like as in, let's separate out the problem of optimizing the objective versus defining the wrong objective. And I think the problem you're getting at is a very important one, and that's kind of like defining the wrong objective, and that's like maybe a little bit different, but tied to the problem of how we optimize that. So I think this is just saying that assuming that the problem is correct, how do you optimize it? And then there's a question of like, is the problem correct, right? And that's often connected to things like inverse RL and things. So we'll talk about reward specification towards the end of the class. Okay. It's tricky because you have to account for its impact on like many steps in the future. And so it's hard to like classify whether something like if you don't have a density model, And so if you have a density model, you could say, okay, this was like really low density under the current transition. You knew like what the probability is going to be, you could say, okay, this is not weight it down. But you don't typically have that because you just have sampling access. And so it becomes tricky to like downweight unlucky samples. So what people often do in RL is either they like try to estimate a density model. So they'll try to like build a density model of like how transitions happen. And then use that to like avoid risky things. So like you do risk sensitive objective stuff. Like that typically helps deal with it, but it's like much more complicated.
Practically, do we have to keep updating the sum of the words as the policy gets up?
Yes, because it's important that you do it on the states and actions that were in your current trajectory. Right, so you have to like compute them on the states and actions in your current trajectory. You can't just compute them beforehand. Because the like trajectories you're going to take are different. Right? And so they have to be done on the fly.
This problem of high variance is inherent to not the objective, but the fact that we're using the gradients.
Correct. And the fact that we're using zeroth order gradient descent, which means that we're not using the gradients to the rewards. We're just like sampling a bunch of trajectories and then just waiting. Okay, so this is what makes policy gradients often unstable. In your homework, you'll see that you run it and like 10 times you run it, it's going to vary 10 different times. And makes it highly unstable, requires huge batch size, and lots of samples. Right, so this is a single sample estimator. What we actually want is something which is like a multi-sample estimator, right? So if I want to know if an action is good, I don't want to just take one sample. I want to take many samples which all share the same action. And then I can know if something is good. So if I, yeah.
So you should have 3 inputs for each.
Hmm.
Okay, if you track it, it's like
In exact form, yes. With function approximation, it's recent. So this is what like the next week we'll talk about active critic methods. What active critic methods do is they try to like use function approximation to estimate this. So there's 2 issues in estimating this, right? Like the first issue is that in a continuous space, you never end up in exactly the same place. And so you never have 3 things like this at all. And the second is the thing you're saying, the branching factor might become crazy. So what active critic methods try to do is try to make this like tractable. Yeah, good question, right? So what we really want is this thing, but like, remind me of your name? Andy. Like Andy was saying, this is like hard to do in continuous spaces, long horizons, right? And so we're going to have a whole lecture on that. It's going to be hard, but let's try to see how far we can get away with us doing that. So we still want to lower the variance of this estimator without actually having to compute this. Right? So this is what we really want in the future, but let's see how far we can get without having to compute it, because computing that is like a pain in the ass. Okay, so the first thing we're going to think about is how do we deal with this fact that you're coupling together all the actions, right? And so when I mean coupling together all the actions, as I was saying, if you have different actions at different steps, you really don't want to have to couple together all of them, because then the outcomes all get tied together, right? So if you look at this objective, essentially, you're taking the sum of rewards along the entire trajectory, and you're like tying the fate of all the log props and all the time steps to the sum of rewards in that whole trajectory, which means that, okay, like, it's like tying together a bunch of people with a rope and determining all their fate by the same thing, right? It's like, why do you have to do that, right? And you have to do that because actions determine future state, right? So you cannot you can't treat them as independent like you do. Like we did in supervised learning, but it was bad for the same reason. Like actions determine future state, and so in RL you can't just ignore the dependence on future states. But what you can do is you can ignore the dependence on past states, right? And so what we're going to do is we're going to say that, our trajectory return depends on currently the past and the future, but like I can't affect the past, right? So I can only affect the future. Like time only goes one way. And so I really don't need to couple with the outcomes from the past. I just need to couple with the outcomes from the future, right? So right now, it's important to notice that this is a sum like this. And this thing is over all the time steps, and this thing is over all the time steps, right? And so every single time step is multiplied with the sum over the whole trajectory, right? So even if I have if I have this thing, it's multiplied by the sum of rewards in that whole trajectory, which is like unnecessarily coupling it to the past. Who cares about the past, right? I just want to say I'm at this state. It's a Markovian. I don't care about the past. I just care about the future. So I don't need to couple my outcomes to everything in the past. So how do I get rid of dependence of the past? T prime to T. Perfect. Yeah, so you just set T prime to T and you ignore terms in the past, right? So you can derive that this gives you exactly the same objective under the Markov property. So the Markov property says you don't depend, the past doesn't depend on the future, conditioned on the present, right? And so essentially, intuitively, all you're saying is that I want to compute the best action in the future. Who cares about what happened in the past? Because I'm conditioned on the present, right? And so all you do in your policy gradient is rather than saddling this guy to the sum of rewards of everything in the past, you only saddle it to sum of rewards of things in the future, right? And so what you're going to do in practice then is rather than computing the sum of rewards in all the trajectories, you're going to compute the sum of rewards in the future. So this is what you call return to go, right? So those of you who do like LQR, etc., this is kind of return to go. So the nice part about this is that you're only computing the return to go. So you've like decoupled your variance. Now you could have like catastrophically bad events over here, but you decouple your variance from those catastrophically bad events. So you're like better off. So that's going to help in your homework. You'll see that's going to help with your sample efficiency and it's going to help with your stability. Okay, that's the first idea. Does that make sense? Okay, solid. We are at 12:50. So how about I think this will take a little more time. So how about we leave this to Tuesday? But yeah, thank you all for attending. And happy to take questions.